Okay, so how's it going, everyone? To get started here, we're actually going to look at a drag race. Um, so believe it or not, all five of these vehicles, and in fact a couple more, have actually all competed in a drag race before. What I want you to do is I want you to try to not figure out. I want you to give a guess as to which one of these five vehicles would win in a drag race. We have an F-16 fighter jet. We have one, which is a Formula One car. We have another one that is a motorcycle. We have another one that is a Tesla Model S, which we've looked at in the past. That is also very fast. And then we have, of course, an Aston Martin Vantage, just a classic, like very powerful, very powerful sports car, very expensive. So let's see if we can figure out, or not figure out. Let's see if we can, guess which one of these would be the fastest. I think I saw you walking your dog near the McLaren dealership. So yeah, I live right next to them. I live right next to I live like next to the McLaren dealership, which is also right next to the Tesla dealership, which is also right next to the Volvo dealership. So there's like three of them like right there. So I live like right next to there. So I don't know if you're talking about the one that I'm talking about, but I live like right there. Yeah. So every day I just walk and I just see the McLarens that I will never buy. Goals in life. Okay, so which the following. Okay, so we got 14 out of 19 people have already responded. This class's votes are much more spread out. Fifth period was literally just like it was two vehicles. Everyone picked one of these two. It was almost a tie, and nobody picked the other three. Here it's much more spread out. We got a lot more like ideas bouncing around here. A lot more spread out. So out of 15 out of 19 people have already responded. So which one do you think is going to win in the drag race? There actually are, so in this drag race, there actually were a few other vehicles. There was a private jet. There was another like two or three more sports cars. But we're only going to look at these five because I think these five are the most fun. We got a fighter jet, Formula One car, motorcycle, Model S, or an Aston Martin Vantage. It's very interesting. It's a very fun race to watch. Very, very fun. So we have almost everyone has responded. We just need a couple more people. So far, it looks pretty spread out. There's no clear winner, but we do have one particular vehicle that is the most popular. 18 and 19, we're just missing one more person to cast their vote. Yeah, so I mean, we do have a little bit of a tie here between two things, but for the most part, they're all pretty spread out. Let's take another minute or so. If you're just joining, I want you to pick one of these five vehicles. Which one do you think would win in a drag race? An F-16 fighter jet, a Formula One car, a motorcycle, a Model S, or an Aston Martin Vantage? If you want to buy me one of these cars, I'd very much appreciate it. I'm down. I'll take it. I'm not too proud. Let's take another few more seconds. Most people have responded. If you're one of the three who hasn't responded, please do so. Take another 10 seconds, and then we will move on to the video itself, and we will see which one of these actually won. Okay, so we're just for the salary of a teacher in California who's been teaching for 20 years, it can buy used tuition. Oh, that's a rip. That's a rip right there. Okay, so actually everyone was responding. Great, that's very cool. Okay, so we're gonna take a look at this video here, and we're gonna see which one of these actually will win in a drag race. Quite a few different vehicles here. So we have, as the video is loading, we have 6 people who picked the fighter jet, 6 people picked the Model S, 5 people picked the Formula One car, 4 people picked the motorcycle, 2 people picked an Aston Martin Vantage. So they're pretty spread out, very, very spread out. Fifth period only picked the fighter jet and the Formula One car. So I'm very curious to see. So as you can tell here, the motorcycle won, but just barely, followed by the fighter jet, followed by the Tesla, followed by some other cars, which we don't care about. But to see, if you want to see the margin of victory here, it's very, very, very small. I'm going to try to pause it right there. Okay. So it's a very small margin. We're talking like maybe like 5 feet or so. And then the fighter jet comes in third. Vroom. Yes, very, very vroom. Okay. So the motorcycle did win, which I know. So actually, a good amount of people have said the motorcycle, but most people actually thought the fighter jet. So what I want you to do here is I want you to try to come up with, and in groups or individually, I want you to try to come up with an explanation as to why the motorcycle won. Because most people did not pick the motorcycle to win. So why did the motorcycle win? Because that's kind of an interesting question. So in your groups or individually, I'm gonna let you decide what you want to do. Try to come up with an explanation as to why the motorcycle won. Okay, so let's take a look at, so I've heard some good analysis from people on why the motorcycle won. I'm going to try to show my perspective, or just sort of give you my thoughts on it, and let's see if we can try to come up with some explanations themselves. So I'm going to switch my view to the board here, and what I'm going to do is I'm going to see if I can order some things around to see if we can put them in an order that makes sense. So what I'm going to do is I'm going to try to order things um, by I guess the place. So like first place, second place. And then I'm going to call the vehicle name. So first place was our motorcycle. Second place was the Formula One car. Third place was the fighter jet. Fourth place was, I think, the Tesla, if I remember correctly. And I think fifth place was the, I want to say it was the private jet. I think sixth place was the. I'm going to include the private jet here just so it's cool to sort of analyze it. Okay. So these are our sort of, and there's a couple other vehicles in here, but these are the ones we're going to look at here. So now what I'm going to do is I'm going to take a look at analyzing one other thing. Let's look at the vehicles in mass. Basically, how heavy it is, how big it is. Motorcycle here is, and now what I'm going to do is I'm going to order it by lightest to heaviest. So first is going to be lightest, sixth is going to be heaviest. So I think the motorcycle is the lightest, so I'm going to put it first. The Formula One car, I think, is the second lightest. So Formula One cars are constructed to be very, very, very light. They're made of very light materials. So the Formula One car is definitely going to be second. I think out of the other ones, I think the Tesla and the Aston Martin are going to be sort of a wash. Teslas are pretty heavy because of the batteries. I don't know how heavy an Aston Martin is, but I'm going to take a stab and I'm going to say the Tesla was the third heaviest. I'm going to say the Aston Martin was the fourth. I'm going to say the fighter jets was the fifth. I'm going to say the fighter jets was the sixth. So from here, let's see if we can try to use these to see if we can construct a relationship between the mass of the object and how fast it was. And so if we take a look here, obviously the data is not perfect, but as you see, the fastest two spots here are with the lightest cars. And then there's a general trend. The fighter jet, which is heavier, which is lighter than the private jet, did better. The Tesla, which is lighter than the Aston Martin, did better. So there's sort of a general trend where the lighter the object is, the faster it was. Now there was a couple of things that were a little bit, out of place, but for the most part, there's the general trend holds true. Now let's look at one other thing, and what we're going to do is let's call this force or energy. The idea is basically how much more. So I think the general trend is that the more, I'm actually not sure how to rank these. So okay, I know we're just gonna skip the force part. I'm not sure how to rank these. I know the fighter jets probably have the most force here. I don't know how much more force Formula One car. But for the most part, if we look at masses here, the general trend is that the lighter an object, the heavier it is. Which from what I understand from what our analysis was, most people seem to agree here. We think the motorcycle won because it was the lightest. So we're going to use this idea to talk about gravity, because that's where we left off last time. And we're going to use this very important idea, the fact that the lighter objects tend to accelerate more when we talk about gravity as well. So going back to sort of the motorcycle here, we are going to talk about, go back and talk about gravity. So where we left off last time was that the Earth and you both exert the same amount of force on each other. So you exert a certain amount of gravitational force on the Earth, and the Earth exerts a certain amount of gravitational force on you. But the two forces are equal and opposite. And this is, and when I sort of was saying like, hey, why do we think this is the case? Why are the two forces equal? It's pretty hard to understand. But the reason behind it is because it's something called Newton's third law. So this is sort of a law that relates to forces. And this law states that for every force, there is going to be an equal and opposite force against it. So if object A pushes against object B with a certain force, object B will exert a force on A with the same in magnitude, but in the opposite direction. So basically, when the Earth and you are pulling on each other via gravity, the Earth is pulling on you. You are pulling on the Earth with the same magnitude of the force, but in the opposite direction. Which sort of explains why, mathematically, you and the Earth have the same amount of force on each other. So this is what we call an action-reaction force, or equal and opposite forces. The idea that when you apply a force, there's an equal amount of force being applied to you in the opposite direction. What I want you to do is I want you to see if you can come up with 3 examples of equal and opposite forces, which we sometimes also call action-reaction forces. So I'm going to put you in your groups here, and I want you to see if you can come up with 3 examples of equal and opposite forces, which we also sometimes call action-reaction forces. So what I want you guys to do now is, guys, I want you in the chat, I want you to type in one example of an action reaction force that you came up with. I'll give you about a minute to do so. So whatever action reaction force you came up with, I want you to type it in the chat, and then around 10:49, I'm going to tell you to hit enter, and we'll see how many action reaction forces we can come up with. So I heard quite a few, so I expect quite a few responses here. So I'll give you about a minute or so. Type in your action reaction force that you came up with. As you can type in more if you came up with more than one. Um, but let's see how many action reaction forces we can come up with. All right, 20 more seconds. All right, in 3 seconds, hit enter. 2, 1, hit enter. Let's get as many ideas as we can. Ooh, we got a bunch, we got a bunch. We got a rowing a boat. You're pushing the water backward and the water is being pushed against you. Great example of an action reaction force. A swimmer swimming forward, great example because you're pushing back on the water and the water pushes back on you. Great example. Pushing a cart, shopping cart, great example. So if you think about it, like if you push really hard on the shopping cart, right, the shopping cart is going to push really hard on you. Your hands are going to hurt a little bit. Swimming, great example. Swimming. Walking, great example because when you're walking, you're pushing on the ground and the ground is going to be pushing you. Soccer ball hitting a goalpost, great example. When you kick a soccer ball and it hits a goalpost, the soccer ball is going to hit the goalpost, and the goalpost is going to reflect it backwards. Magnets are one of the coolest examples of action reaction forces. The two magnets are both exerting force on each other, equal and opposite. That's one of the coolest examples. Eating beans. I'm not sure how eating beans is an action reaction force. It is funny. I'm not. If you can explain to me how it's an action reaction force, I definitely think that could work. I can't really think of it how. Ice skating. Ice skating. If you are, yeah. So to ice skate, you have to push onto the ice, and then that allows you to go forward because the ice is going to push back on you. A ball bouncing. The ball applies a force to the ground, and the ground applies an equal and opposite reaction that propels the ball into the air. Great example. So these are all some really good examples of action reaction forces. And this is exactly how the force of gravity works. Gravity is also an action reaction force. When you pull on something gravitationally, that same object is going to pull on you gravitationally. So now that we sort of get an idea of why, we have the why forces of gravity act on all objects, why they're equal to each other, the question is, why doesn't the Earth move? Because if we jump up, right, we're the ones falling. So why doesn't the Earth fall? So this sort of relates to the warm up we did with the motorcycle. So the main idea is that the force acting on an object is equal to its mass times its acceleration. So if I'm applying a certain amount of force to an object, that amount of force is going to equal the object's mass and its acceleration, right? So if I'm applying the same force to an object, right, the more massive it is, the less acceleration it's going to have. The less massive it is, the more acceleration it's going to have. So with a motorcycle, right, because it has very little mass, you don't need a lot of force to make it accelerate very quickly. On the flip side, for a private jet, because it has a lot of mass, that means if you apply the same amount of force, it's not going to have a lot of acceleration. So this is a very important equation that you should definitely write down. F equals ma, very important equation. One of the cornerstones of physics is this equation, F equals ma, which we'll use in a second. So definitely remember this equation. So yeah, that's pretty much, so in order to calculate the force of an object, you can use its mass times acceleration. And then there's a relationship between these quantities here. If you apply a lot of force, right, that means your object can accelerate a lot faster. If you don't apply a lot of force, it means your object it won't accelerate as much. And the mass also affects that acceleration. The more massive it is, the less it's going to accelerate. The less massive it is, the more it's going to accelerate. So there's definitely a relationship between these quantities. It's very important. So what we're going to do is we're going to use this equation, and we're actually going to try to calculate how much the force of how much we actually accelerate due to gravity. So last time we calculated a force of gravity, I'm going to write it down again. I think it was last time what we calculated is that both you and the Earth both exert a force of 734 newtons, if I remember correctly. What I want you to do is I want you to use this force in the equation F equals ma, and I want you to calculate how much acceleration you experience due to the force of gravity and how much acceleration that the Earth experiences due to the same force of gravity. So you have a mass of 75 kilograms. The Earth has a mass of 5.97 times 10 to the 24th kilograms. So use the mass that you have and the mass that the Earth has, and I want you to calculate how much acceleration you experience if you both are experiencing a force of 734 newtons. So make sure you have your force written down, 734. Make sure you have your equation written down, F equals ma. And I want you to calculate how much acceleration you experience and how much acceleration that the Earth experiences. So once you have the force written down, once you have the equation written down, you can join your breakout group and you can work with your group to see if you can figure out how much acceleration that you experience, how much acceleration that the Earth experiences. Andy, you have the force written down? You have the force written So what we're going to do now is we are going to do this problem mathematically, and then we're going to talk about what this means to what it means to have the accelerations. So I want to do it on the board here to show you how you do it. So the equation we're going to use is F equals ma. So the force acting on the object is equal to its mass times its acceleration. So the force that we are exerting on the Earth is, so this, we're going to look at our first at our acceleration. So the force that the Earth exerts on us, which we found, was 734. And this should equal our mass times our acceleration. So how much is our mass? Well, our mass here is 75 kilograms. So the force that the Earth exerts on us, 734, should equal our mass, 75, times our acceleration. So how do we solve this? We just divide both sides by 75. And so we get that our acceleration is 9.8 seconds squared. So notice how this is very similar to something we used previously. So previously, when I said, hey, let's calculate the potential energy, what you did is something like use something like G is equal to 10. So this G is actually a measurement of the gravitational acceleration. So this is actually where the G comes from. So this G is actually a rounded number. The correct, mathematically correct answer is 9.8. We use G to make our life similar, but the actual value is 9.8. And this is where the G comes from. It's actually a measurement of how much we accelerate when we're on Earth. So we took our force, the amount of force that the Earth exerts on us, and we figured out how much acceleration that it converts to. We actually found that we accelerate at 9.8 meters per second squared. So that's how much we accelerate when we're on Earth. Let's figure out how much the Earth accelerates. Okay, so first off, we use the same equation, F equals ma. Now we know the mass of the Earth. The mass of the Earth is given 5.97. We're trying to find the acceleration, so we don't know the acceleration. And the question is, what force should we work? Well, here's where we use the term, here's where we'll use what we just learned about action-reaction forces, about equal and opposite. So if the Earth is exerting a force of 734 newtons on us, gravitationally, that means we have to exert the same amount of force on the Earth. So that means that if the Earth pulls us with a force of 734, we have to pull the Earth with a force of 734 as well. So the Earth is feeling a force of 734 newtons, and that's going to equal its mass, which is pi. So to solve this, we do the exact same thing. We divide both sides by 5.7. A little bit of, and this is going to require a little bit of calculator skills because exponents are not easy to work with a calculator. Well, if you do this correctly, you'll get that your acceleration should be something like 1.2 or something times 10 to the negative 22. Something like that. So if you don't know how to interpret this, well, the thing with a negative exponent is that basically tells you how many zeros are in the decimal. So something like 10 to the negative 22 is going to look something like this, 0.000000000, where there's 22 zeros in total. And eventually we'll have 1.2. So basically there are 22 zeros before we have our 1.2. So this is a very, if you don't know how big this is a very small number. Like basically, if you think of like 0.1 is very small, 0.01 is very small, 0.001 is even smaller. This is a tiny, 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 tiny. So essentially, right, if this is how much acceleration we experience, this is how much acceleration the Earth experiences. And it's so small, the Earth basically doesn't move at all. We move quite a bit. What this means is that every time, the Earth, what this means is that every second, we're speeding up by 9.8 meters per second. What this means is that every second, the Earth is speeding up by 0.0000012 meters per second. So it's so small that the Earth is basically stationary. Now the Earth is still, in actuality and technically moving, but the amount it's moving by is so small that we can consider it stationary without actually having any sort of impact. So this is why the Earth doesn't really move when we do anything, but this is why we move when the Earth does something. And that's because, right, even though the forces are the same, the fact that the Earth's mass is so much bigger than ours means that the Earth is basically going to experience no acceleration at all. Okay, so next class, we are going to start using our equations for centripetal force and gravitational force to do a derivation. But I think for the rest of the class, I'm just going to just quickly just talk about revolutions, and we'll continue this next class. So how does this relate to orbital motion? Because the main topic of this unit is elliptical orbits. So how does the mass and acceleration sort of come into play here? Well, one thing we want to know is we want to know what a revolution is. So we basically want to know what does it mean to have an orbit? How long does it take to have an orbit? And this is what we call revolution. This means that an object is moving around another object. So basically, when we measure a revolution, especially if we measure the revolution of the Earth around the Sun, we use the unit a year. And a year is just basically how long does it take for the Earth to complete one revolution around the Sun. And that is 365.24 days. So basically, it takes the Earth 365 days to go around the Sun once. So that's a measurement of a revolution. And we can also measure the revolution of a clock. We can measure the revolution of a merry-go-round. We can measure the revolution of any rotating object. So what we'll want to know is we'll want to discuss on Friday how we can measure the revolution time of an object, and we're going to want to figure out how we can measure the revolution time of an object. But we'll continue that on Friday. Yeah, so that's pretty much it today. I think we finished a little early, but that's okay. So no homework. We're going to continue this on Friday. So if you're on Zoom, you're free to go, and I'll see you guys on Friday. Yeah.
Thank you, Mr. Hu.
Thank you.